So in yesterday's class we started looking at output stages. So I assume you have reviewed the fractional band gap. So I won't review that because we have moved on to a new topic. So we started looking at what types of output stages you have, and we defined it based on the portion of the cycle over which the amplifier transistor conducts, right? So we just took the example of a very simple common source, and we compared the bias to the amplitude, and in the case of the MOSFET, the VT. Okay? And if it for class A, the conduction angle is 360 degrees. For class B, the conduction angle is 180 degrees, and therefore if you see class A, both the current and voltage waveforms will be sinusoidal, whereas for class B, the voltage waveform will be sinusoidal. Hopefully that's what you want to get. The current waveform, on the other hand, will look like a half sine wave, a rectified sine wave. In the case of class C, your conduction angle is even less than 180 degrees. Okay, which means it doesn't even conduct for half the cycle, it conducts maybe for a very small portion of the cycle. Okay, so one of the reasons why we move on to these kind of conduction angles is because there is a certain trade-off in these cases between gain, distortion and power efficiency. We are going to look at that over the next few classes. And we started off with the emitter follower output stage, and we tried to find out the conditions for, first of all we tried to draw the input output characteristic, right? And we came up with three cases. In the case of VO greater than 0, we figured out transistor is going to be on and it can swing all the way to VCC minus VSAT 1. The output can swing all the way to VCC minus VSAT 1. Correct? Therefore, the input maximum is nothing but VCC minus VSAT 1 plus VBE 1. And then for VO less than 0, there were two cases. First case is when the load resistance is very large, right? So when the load resistance is very large, what happens? Your output can swing all the way down to minus VE plus VSAT 2. Correct? Everybody remembers this? And when RL is very small, your output can go all the way to VO equals minus IQ RL. That is the point when the upper transistor cuts off, right? And that is not the most optimum operating point, because you really want to operate at full swing, which means you want to go all the way down to minus VE plus VSAT 2. So you are going to increase the bias current IQ such that you are not limited by Q1 getting cut off. And that's how you get this condition, IQ equals VE minus VSAT 2 over RL. So that is your design point. So that will be the point when Q1 just cuts off, but you get maximum swing, right? So we started drawing the overall transfer characteristic, so we'll complete it today. So let us say we start off with upper end, there's no problem. Q1 goes into saturation. We know these 2 points also. This is VCC minus VSAT 1. This is VCC minus VSAT 1 plus VBE 1. That is the upper point. So there is no confusion there. At the lower end, this is the case when Q2 is saturated. So we'll call that RL1, where RL1 is very large. Okay? And if your bias current is different, you can have a case like this. And then it follows the same thing this way. Okay, if your bias current is less than this value, then Q1 will cut off and your output voltage will be clipped at minus IQ. I'll call this RL2. Minus IQ RL2. Correct? What is this voltage? Minus VE plus VSAT2 plus VBE1, of course, I mean, right? Just note that the VBE1 itself, I mean, when you move along this characteristic, IC1 changes, right? Because I out changes. Why does I out change? Because V out changes. As V out changes, I out changes, therefore IC1 changes, therefore VBE1 will change. So this VBE1 is not the same as this VBE1 because they are at different current levels. Just remember that. Okay, they won't be exactly the same, but in this case, because it's a bipolar, there is not a lot of difference. It will be somewhere around 0.7. It may change by a few tens of millivolts. Okay, in the case of the MOSFET, which we will look at later today, the difference is quite a little bit more pronounced. That's all. Okay, so we have come up with the load curve. Why did we draw this? Because any time you are going to put in an input sinusoid, from this you can calculate how much swing is permitted without distortion, right? So if you apply a sinusoid along this, you can find out how much output swing you have, right? And how much output swing you can tolerate. Okay, what else? Gain is close to 1, so we already know that. Actually, in the case of the bipolar, it's almost exactly equal to 1 because you only have output impedance, which is usually much larger than your 1 over GM. Correct? What is the third parameter? Efficiency and output power, right? Both go hand in hand. Okay, so first let's calculate output power. So let me get that circuit back. What is VCE1? The collector emitter voltage? Nothing but VCC minus V naught. So write it as VCC minus I naught RL equals, what is I naught? Okay, VCC minus IC1 minus IQ times RL. So what this equation gives you is on the transistor characteristic. So based on this equation, you have related the collector emitter voltage of Q1 to the collector current of Q1. Okay, so now you can draw what is called a load line on the ICVC characteristic of the bipolar transistor. You can see how the transistor behaves on this curve based on this relationship. Okay, and again you can draw three sets of load lines. One is when RL is very large, the other is RL when RL is very small, and then one special case of that RL is very small is the optimum case, when you can actually change the bias current IQ to the optimum value. Okay, and that will be the case when you actually get, of course, maximum swing and maximum output power. That is also a important parameter we are interested in. Okay. So let us say I am drawing my ICVCE curve. Let us say this is my quiescent point. Okay, in other words, this is IQ. What is this? What is VCEQ? What is VCEQ? VCC minus V naught. That's right. But we also plotted what V naught is when Vi is 0. It will be very close to 0. Okay, so VCE1 is going to be very close to VCC. Right? You want your output bias very close to 0 because you have plus VCC and minus VCC. The output quiescent point, you are going to bias it close to 0. Correct? So, your VCE1 is going to be very close to VCC. Okay? Okay? So now let me use a different color. So this is the case when if you have RL1 which is very large. What happens when RL is very large? Your output swing, the current never cuts off, and your output swing is just limited by the supplies. Correct? So in other words, so let me call this what is this voltage? Why is this? Let's assume VCC equals VEE. Okay, so it's symmetric supplies. The lower swing, what is the, when RL is very large, what is the maximum swing across the load? How low can the output swing? Minus VE plus VSAT2, right, for large RL. What is VCE1 in that case? It is VCC minus this number. So 2 VCC minus VSAT2. And the transistor never cuts off, right? So the curve will look something like this, right? So if you had to draw VO hat, the peak value, it will be this, the region shown by the brackets, it will be this. The difference between these two will be the maximum swing. Correct? What is this? This will be the maximum current swing. You are at bias quiescent Q. You will get a swing of some IO hat. What is that given by? Well, you know the relation between IC1, IO and IQ. IO is nothing but VO by RL. You already know VO. VO max. You can find out IO max. Is that clear to everyone? Yes or no? No. Yes. Yes. Okay. So this is IO hat. The shaded area. What is the shaded area? The shaded area will give you the power dissipated in the transistor, because you are looking at the area on the IC versus VCE curve, right? IC times VCE will give you the power dissipated in the transistor. Okay, this is for RL1. Suppose you draw the same curve for RL2, which is a very small RL. What will it look like? Slope will be much larger, first of all. Second thing is, it is going to intersect the x-axis, because you know the Q1 cuts off. It looks something like this. This is RL2. Okay? What is this? Let me call this Vx. What is Vx? The absolute value of Vx. Yes, what is that? It's VCC plus IQRL, right? You're starting off from VCC, so the absolute value will be VCC plus IQRL. Correct? The swing is IQRL around the quiescent point. This area will give you the power dissipated. In either of these cases, okay, in either of these cases, you don't get the maximum output power which you are looking for, because you also want this stage, you want to design it such that you get maximum output power. In one case the swing is maximized, but IOM is not necessarily maximized. In the other case, IOM is maximized because you go all the way to cutoff, so it will swing is almost IQ as far as the current is concerned, but your voltage is not maximized. Remember, okay, think about this. In one case your current is getting completely cut off. In the other case is with respect to IQ. Okay, just think about it. So his question is, why are you taking the vertical area instead of the horizontal area, right? So think about it. Okay, think about why that is the case. So now there is a third optimum case, which is, of course, in this case I am going to say it's RL3. It's going to look like this. Right? Where both, okay, in this case I am actually increasing RL3. So I am showing it as changing the RL load resistance. In a real case you would have to change IQ such that that will be the design parameter, not this. But in this case we keep IQ constant and vary RL, because that's what we have been doing. So if you do that, you will simultaneously maximize both the voltage and the current. Okay, that will be the point when Q1 just cuts off, but also the point when Q2 just goes into saturation. What is the average power through the load? What is it? Yeah, but if you do it in terms, write it in terms of VOM hat, IOM hat. What is it? So, or VO hat, IO hat, whatever, the peak values of the, so what we have found out based on the load line and the transfer characteristic are the peak values of output voltage and output current. Now we want to find out the average power with, let us say you design it with RL3. You want to find out the peak, the average output power. VO hat, IO hat by 2. So it's VO hat by root 2 times IO hat by root 2. Okay? And you want to do this for the optimum case. So we'll call that PL max. What is that? What is VO max? VCC minus VSAT. Correct? What is IO max? IQ. Okay? So this is the maximum power delivered to the load. Correct? Is that clear to everyone? What is the current drawn from the supply? What is the power drawn from the supply? I'll assume VCC equals VE in all cases. 2 VCC times IQ. So I'm going to define something called eta C, which is the power conversion efficiency. Which is nothing but the power delivered to the load over power drawn by the power drawn from the supply. In this case, what is eta C max? This is the max power delivered to the load. Correct? And we also know VSAT is typically much smaller than VCC. Okay? So the efficiency of this particular stage is around 25%. So for every milliwatt of power you are delivering to the load, you have to burn 4 milliwatts from supply. Right? Doesn't seem very, this efficiency is actually not very large. Okay? Of course, the advantage is that distortion performance is very good, because if you make sure your swing is such that you spend most of the time in the linear region, you know that input is a voltage is a sinusoid, output voltage is a sinusoid, all output currents are sinusoids. Correct? So you expect your distortion performance to be the best. Okay? Now suppose you draw the current and voltage waveforms. Okay? Through transistor 1. So let us say it looks like this. What is the value? Approximately 2 VCC. We'll neglect VSATs for now. It's a lot easier. This is almost 0. So it's going to swing almost rail to rail as far as VCE1 is concerned. What is IC1 going to look like? Let us say VCE1 looks like this. What is IC1 going to look like? It's going to look like VCE1. Is that right? It's going to look like that? What is it going to have? Phase shift. By how much? 180 degrees? Why is that? Let's go back to this circuit. I am telling you, VCE1 has a peak, goes all the way to 2 VCC. What is I out at that point? Is it maximum or minimum? I out will be minimum, right? When you swing the other way, I out will be maximum. So it will be 180 degree phase shifted. Your I out curve is going to look like this. Sorry, this is IC1. IC1 curve is going to look like this. This is IQ. This will be 2 IQ. This will be 0 in the limiting case. Is that okay? Now if I am going to draw the power dissipated in transistor 1, what is that going to look like in Q1? Multiply them. So what is that going to look like? Here is going to be 0. What is it here? Huh? It's going to be double the frequency. Correct? It's going to look something like this. This is the power dissipated in Q1. Okay? So now, as far as the transistor is concerned, why are we talking about the power dissipated in the transistor? That's the losses, but that's okay. Yeah, so losses is one part. We have already calculated the efficiency. What else is there? You have to worry about the reliability of the transistor, right? So as far as the reliability of the transistor is concerned, you have to worry about the junctions heating up because you have too much current. So this is basically power dissipated as heat in the transistor. Okay, so you have to worry about two parameters now. The average power and the peak power. Okay, the peak power will decide how much your junction heats up, because that is the maximum power dissipated. So that will give you the peak temperature of the junction, right? And the average power will give you over time how much the overall transistor heats up, as well as, of course, like you mentioned, it will give you the power losses in the transistor. So you have to worry about both parameters. What happens if the frequency is very large? The frequency of operation is very large. What happens? So you will be hitting the peaks only. So what will happen is the average and the peak will move closer to each other. So you will start worrying mainly about the average, not about the peaks. It won't be spending at the peaks enough time for it to heat up the junction appreciably. You are more worried about the average value. Okay? Okay, so let's stop here. We'll continue with, so we are done with the emitter follower. Starting tomorrow, we'll look at the source follower. Okay, the same thing with a MOSFET. There are some extra things you have to worry about. Okay, especially with respect to distortion. So we'll look at that tomorrow. So one last thing here, forgot to mention this. Of course, the quiescent power is IQ times VCC. Okay, that is goes without saying.